the first practice set in section 6.1 about momentum and impulses on page 191. And I just worked out a few of these problems and wanted to run over them. They're really simple problems. In the first problem, we have a deer running at a particular speed, and we're asked to calculate its momentum. This is as simple as plugging numbers into this formula and getting an answer. And so it's probably the easiest type of problem that we ever do in this class. I didn't work problem 2 here, but here are my results for A, B, and C. This is a problem about a child on a bike, and the child has a particular mass, and the bike has a particular mass, and they're moving a certain speed and direction. And when you do the calculation, that is simply just multiplying the total mass times the velocity. You get this, and the reason you get this is because you have to observe your significant digits. And so we're only allowed to report 2 significant digits in this problem. When we calculate the momentum of the child and then separately the momentum of the bike, we get these 2 numbers. And you'll notice that when you add those together, you actually get 122. And we would expect that the sum of these 2 momentums would equal this one. And I just want to point out that they do equal this one to the appropriate number of significant digits. When you add these 2 numbers together, you get 122. With 2 significant digits, it becomes 120. That's not exactly how significant digits work when we add, but because we only started with 2 significant digits, we're only allowed 2. Anyways, it is important to notice that these 2 numbers ought to add up to make this one. And then finally, a marginally more challenging problem. You're given a mass and a momentum, and you're asked to find the velocity. We just have to do a very little bit of algebra to rearrange our equation and then substitute and get an answer. So just dealing with the momentum equation at first is pretty simple. But if you go deeper into the section, there's another set of practice problems, and this is about the momentum impulse theorem, or I think that's what they call it. Yeah, the impulse momentum theorem, actually. And that's what this problem is about. So I'm going to work this one first by let's read it here. There's a man, and he's dropping off of a diving board from rest. It's 3 meters above the surface of the water, and then he comes to rest in about a half a second after reaching the water. And they're asking, what's the net force on the diver as he is brought to rest? So when I think about this problem, I think the net force that's acting on this person is really the drag force due to the water that he's falling through. And so we're really concerned with, we've got a few things here. And let me just write down the things that we know. We know that his mass is 82 kilograms. And we know that the diving board is a height of 3.0 meters above the surface of the water. And that the time that this force was acting on him was 0.55 seconds. And that is, in fact, what we're looking for is a force. And they didn't tell us a unit, but we know that forces have units of newtons when we use our SI units, so we'll just leave it there. I'm going to draw a diagram of this situation just to make a little sense of it. Here's our person on the diving board, and they're 3 meters, let's do this, above the water. So this is 3 meters. I'll just label it H. And he's going to be traveling, once he hits the water, he's going to be slowing down. And when he's down here, we know that he's at rest. And because we're really interested in what's happening from here to here, because that's when the force is actually acting on him to slow him down, the force that we're looking for. I need the initial speed right here, and we know that his final speed down here is 0 because he's at rest. So kind of jumping the gun a little bit, but I do know that in a momentum problem, we're going to need some speeds. And what we're really looking for, this is really an impulse problem. The force times time, that's our impulse. That's what an impulse is. And that equals a change in momentum. So if you want to change something's momentum, and that could mean slowing it down, you need to apply a force over a certain amount of time. And so our force is going to be operating in this direction, okay? And let's notice that his initial speed is actually in that direction. So let's expand our formula. F delta t is equal to the final momentum, which is going to be mv final, minus mv initial. And we know that his final momentum is 0 because this final speed is 0. So I can go further. F delta t is equal to a negative mvi. And again, you can just notice that the purpose of the negative sign, or where that ultimately comes from, is that the force that's acting on this person to slow them down is in the opposite direction of the velocity. So we're looking for F. We know delta t. We know m. We don't know v sub I. So we know we have an equation, a single equation with 2 unknowns. Of course, we can't solve for F in this case. So we're going to have to come back to that. But remember, we know this is a conservation of energy problem now, because this person is falling from rest, we're assuming on Earth. And so whatever energy he has up here, I'll just say, let's call this the mechanical energy at A, and this will be B. The mechanical energy at A is equal to the mechanical energy at B. Clean that up a little. And at this point, he's not moving at all. There's no elastic spring energy, potential energy, that is. And so all of the energy in this system is mgh. And once he falls to a height of 0, all of his mechanical energy is going to be 1/2, and I'm going to call it v sub 1/2 mv sub I squared. So I've got these formulas here. And now I know what g is, of course. We'll add that to the list of things that we know, 9.81 meters per second squared. And we know what h is. We just don't know what v is. So we can solve this equation for v sub I. First, cancel out those m's, multiply both sides by 2, and take the square root, and you get 2gh square rooted equals the speed. And so from here and here, right, we can put all this together and say F delta t equals negative m square root of 2gh, and a little bit of work to get the F by itself. F equals negative m square root of 2gh divided by delta t. And so when I plug all this stuff in, negative 82 kilograms times the square root of 2 times 9.81 meters per second squared times 3.0 meters, all divided by the change in time, which is 0.55 seconds, and we get a force of negative 82 times the square root of 2 times 9.81 times 3, and then I'm going to divide that by 0.55. And I get a negative 1,143.8. I'm only allowed 2 significant digits, so negative 1,100 newtons. And I might, I just want to interpret the negative sign a little bit. And so maybe instead of just saying negative 1,100 newtons, I'm going to say F equals 1,100 newtons up. And that's my solution to this problem. So what's challenging about this is that we got to go back and remember that we can use energy in a momentum problem. Ultimately, this is a momentum problem, and it's in the momentum section of the book. But we did need to conserve energy in order to find that velocity that this diver hits the water with. And once we did that, we were able to solve the problem to get the force.